Welcome to this Alan Talks Tech presentation on beamforming and the use of millimeter wavelengths for 5G. If you'd like to learn more about how to test these technologies, please visit our website at spiron.com. If you'd like to learn more about other technologies, including 5G and other subjects such as Wi-Fi, please visit my YouTube channel, Alan Talks Tech. And if you'd like to get a little bit more detail on 5G and Wi-Fi, please visit my wiki at alantestwiki.pbworks.com. So we're going to face some interesting challenges when moving to the next generation of cell phone networks, i.e. 5G. Today, most cell phone networks around the world are operating in the frequency range of about 600 megahertz to around 2.7 gigahertz. But in the future, 5G networks will most probably start at around 3.5 gig, going up in the near term to around 28.5, just over 30 gig. Long term, we'll have to move even further up the frequency range, well above 60 gigahertz, possibly well above 100 gigahertz and beyond. But with the use of these high frequencies comes some interesting problems. Not so much in the 3.5 gig range, but definitely when we get to the 28.5 gig, 30 gig range, some interesting challenges. One of these challenges is rain fade. Literally, rain can attenuate the signal. You may have noticed this, for example, if you get your television via a satellite operator. When you have, for example, a very heavy rain shower, your signal may literally get washed out. But other things can attenuate the signals as well. For example, the foliage on trees can have a significant effect on the propagation of these high frequencies. Even the UV tinting on windows on large buildings can actually attenuate the signals. So, how are we going to get around this problem? Well, one potential method to get around this is to use massive MIMO. With the use of massive MIMO, we'll be able to use more advanced beamforming techniques to punch the signal through. But if, for example, you've got some heavy foliage between you and the nearest cell tower, you may still find, even with advanced beamforming, it's not enough to penetrate that foliage. So literally, to get around this problem, we're going to have to deploy many smaller E-node Bs. Each of these E-node Bs are going to have to be interconnected with a high-performance backbone. These high-performance interconnect links may be well running in the 60 gigahertz range. Of course, wherever possible, we use fiber, but due to the sheer size of deployment, I suspect in the future many of these cell sites will be backhauled using very high-frequency RF. Why are we moving to these very high frequencies? Well, it's basically all about bandwidth. Today, in a typical LTE network, the maximum number of channels that can be aggregated together are 5. Each one of these channels in an LTE-A network is about 20 megahertz. That gives you a total capacity of 100 megahertz. In reality, though, most of the carriers today can only provide up to about 3 channels for aggregation. There is some talk that during 2018 and late 2017, some of the carriers may be providing 4-channel aggregation. But at best, it's going to give you 60 to 80 megahertz of bandwidth. 5G is a quantum leap. To provide the throughputs required, 1 gig to perhaps 10 gig in the near future, we're going to have to provide much more bandwidth. We'll be providing up to 800 megahertz of bandwidth, for example, during 2018, with some of the silicon that is planned to literally roll off the shelves. To get to 800 megahertz of bandwidth, each one of the channels in the new 5G networks will be 100 megahertz. And with these new services, it'll be possible in the first wave of silicon to aggregate up to 8 of these channels together to give us a total capacity of 800 megahertz. To get that type of bandwidth, though, we do have to move to these higher frequencies. Operating in the range of 600 megahertz to 2.7 gig, there simply isn't enough spectrum, there isn't enough capacity to provide this type of bandwidth. Massive MIMO is definitely going to help. With massive MIMO arrays of up to 256 antennas, we'll be able to beamform to individual devices. We'll even be able to track devices, and testing is already underway with high-speed trains where we can actually track the high-speed train potentially moving up to 500 kilometers an hour. Currently, most systems deployed can only beamform in the horizontal, but with FD MIMO or 3D beamforming, we'll have a lot more flexibility. Not only will we be able to beamform in the horizontal, but we'll be able to beamform vertically as well to give us that 3D effect or full dimension MIMO. So for example, a transmitter located on a lamppost will be able to beam to the top of the building, to the middle of the building, or down to the entrance. However, even with this advanced beamforming, it's suspected that many of these buildings will have to have localized transceivers coupled to antennas on the outside of the building to re-radiate the signal internally. Because even with the beamforming, it just won't be possible to penetrate the UV coating. Thank you for watching this presentation on Alan Talks Tech on beamforming and the use of millimeter wavelengths for 5G. Again, if you'd like to get a little bit more information on how to test these technologies, please visit our website at spirent.com. And don't forget to view my YouTube channel, Alan Talks Tech, for other technology introductions. And last but not least, if you'd like to get a little bit more information on 5G technologies and Wi-Fi, which is going to be a very important component of 5G, please visit my wiki at alantestwiki.pbworks.com. Once again, thank you for viewing.